So I know this class is called pre-calculus, but we are going to give just one day to touch a little bit on statistics. So we're going to do a little bit of counting problems, just a little bit of probability. And before we look at that, we have to learn something called factorial, which shows up in some of those problems. So this exclamation point here, as the symbol we use for factorial, means a multiplication problem where we take the number and then all the numbers smaller all the way down to 1 and multiply them all together. So if you look at this example here, we're not just really excited about the number 5. This 5 exclamation point is just 5 factorial. And so what it means is we do 5 times 4 times 3 times 2, and then stop at 1, and then just multiply all those together. So 20 times 6, that would be 120. Okay, and this is in your calculator as well. Let me show you where to find that. So if we type the number 5 here, and then, kind of funny enough, we haven't used the math button that often in a math class, but if you push the math button here, then we want to go over to PRB. So you could have just hit the left arrow as well to go over to PRB, and it's this fourth choice here. Again, factorial shows up a fair amount in probability problems. So we can just hit the fourth button or hit the number 4 button or scroll down. 5 factorial gives us 120. All right, and so of course this next problem we could just type it in our calculator, but there's actually a pretty simple way to do this without our calculator. If this was on a no calculator section of a test, and we wouldn't, of course, want to actually find 10 factorial. That would be a pretty large number. We wouldn't want to find 8 factorial. That would be pretty large. Let's start writing this out and see if you can see what's going to happen. So 10 factorial would be 10 times 9 times 8 times 7. Let me just kind of put ... there. Getting a little tired of writing all those numbers. You get the idea. And then 8 factorial, that would be 8 times 7. I'm just going to say ... Well, take a look at that. Do you see what's going to happen now? So in the numerator here, we have the 8 times 7 times 6 times 5 all the way down. And the denominator, we have 8 times 7 times 6 all the way down. All this stuff is going to cancel. The 8s are going to cancel. There's no pluses or minuses, so there's nothing getting in the way of canceling. We can just cancel these out. The 6, 5, 4, 3, 2, 1, both numerator and denominator are going to cancel out. All we have left is the 10 times 9. It's just 90. Whoops, sorry, I don't know what's going on here with my writing. Sorry about that. This equals 90. All right, so this kind of idea of factorial cancellation actually shows up a fair amount in calculus when you're dealing with something called power series and something called the ratio test, things that you have no idea what are right now, but this idea will come in handy. And we're also going to look at what that would look like with variables. So you'll do that a lot in calculus as well. But first, let me back up a second and take a look at this 0 factorial being 1. So the thing is, if n is 0, this definition doesn't make sense, right? We're supposed to start with a number bigger than 1 and then multiply smaller numbers down to 1. So what does that even mean for 0? It doesn't seem to make sense with this definition. The thing is, for a lot of the formulas that we use factorial in, we have to have a definition for 0 for them to work. So we need to have a 0 factorial. And 0 factorial is actually going to equal 1. A lot of people would think it would be 0, but it's 1. So I'll prove it to you. I mean, first of all, I can show you in the calculator. If we do 0 and the left arrow and the fourth choice, 0 factorial is 1. Right? Let me go ahead and prove it to you, though. So what I'm going to do is I'm going to look at n factorial over n. And then let's try to do this cancellation idea in factorial with a variable. Okay? So n factorial, well, that would be n. And then the next smallest number after n is n minus 1. How do you get to the next smaller number? You just subtract 1 every time, right? From 5 to 4 to 3 to 2 to 1, you subtract 1. So n, and then we subtract 1, we get n minus 1. We subtract 1 again, we get n minus 2. Subtract 1 again, n minus 3, and so on. And then this is all going to be divided by n, Well, take a look at what happens. The n's cancel out, and we just have all of this left here. We have n minus 1, n minus 2, n minus 3, and so on. Well, what is that? N minus 1 times the next smallest number times the next smallest number, going on all the way down to 1, of course, right? Well, that's n minus 1 factorial. So n factorial over n is going to equal n minus 1 factorial. I'm going to use that statement. I'm going to use the fact that n factorial over n equals n minus 1 factorial. I'm going to use that to prove that 0 factorial has to be 1. Let's look at when n equals a particular number. All right, let's think about what number we want to use. If I make n equal 0, well, then I'd have 0 factorial. I don't know what 0 factorial is. I'd be dividing by 0. That's undefined. I get negative 1 factorial. That's not what I want. I want to make n equal 1. So then I'll have 0 factorial here, and I'll know what this is. Let's see what happens when n equals 1. Over here, I would have 1 factorial over 1. And then over here, 1 minus 1 is 0. So over here, I'd have 0 factorial. So this part right here is this, and then that is that right there. Well, was 1 factorial? You start at 1, and then there's no other smaller number, so you just stop at 1. So 1 by itself, multiplied by nothing else. So we just get 1, and then over 1 equals 0 factorial. So that means that 1 has to equal 0 factorial. There we go, we proved it. Okay. Now I do all this just to, one to make sure that you know that 0 factorial is 1. You don't need to know the proof or be able to prove it or anything like that. You just really need to make sure you know that 0 factorial is 1. That's important to know. But also just to start showing you a little bit of this idea of canceling out factorial with variables. That is something you'll do a fair amount of if you take AP Calculus. So let's try this example here. Let's try doing some more factorial cancellation with a variable. Okay, so let's start to write this out a little bit. Okay, so I'm going to start with 2n. And then the thing you always have to remember is in factorial, the numbers get smaller. That's one thing that people will mess up on these. We need the numbers to get smaller, so we need to subtract 1. So 2n minus 1, 2n minus 2, and so on. All right, that's going to be the numerator. And then the denominator, we're going to have 2n plus 2. And then we subtract 1 to get to the next smaller number. That's 2n plus 1. And then subtract 1, we're at 2n. Keep subtracting 1. Remember factorial, the numbers get smaller. And so on. All right. Well, as we write this out, again, we should always see a bunch of nice cancellation here. The 2n's cancel out. The 2n minus 1s cancel out. The 2n minus 2s cancel out. Everything all the way down to 1 cancels out. And we're just left with the 2n plus 2 and the 2n plus 1. Now be careful though, where were they? Remember, we were dealing with a fraction here. Where were those factors that are left? They were in the denominator, right? So they have to stay in the denominator. We've got an empty numerator. That's 1 right there. So 1 over that, and then we should simplify this here. On the test, the directions would be simplify. Simplify, we do have to multiply it out. So we'd have 4n squared, and then we'd have 4n plus 2n, that's 6n, and then plus 2. All right, so that's factorial. All right, so now let's take a look at some of these word problems. So the first thing we're going to do before we do probability is we're just going to count things. You might think that you've been counting since, what, I don't know, kindergarten, first grade. But we're not just going to count 1, 2, 3, 4. We're going to try to figure out the number of possibilities of things in some word problems. So let's say that we've got 5 shirts, 3 pairs of pants, and 2 hats. How many different outfits can you wear? Maybe you're on vacation. You're looking at what's in your suitcase and trying to think how many different options you've got here. So what we do here is something called the fundamental counting principle. So the fundamental counting principle says if we have something like this where we can, I like to think of it kind of like slots. We've got different slots that we have to fill in, and the slots have to be separate. So like we've got shirts is one slot here, right? And then we've got pants is another slot here. They have to be separate. You have to be able to tell the difference between these. Hopefully you can tell the difference between a shirt and a pair of pants. And those are not interchangeable, right? You can't really wear a pair of pants as a shirt, at least not very successfully. So you have to be able to tell the difference between these. These have to be completely different things, right? And then we've got another slot for our hat. So we look at those different kind of slots that we have to fill in, and then we look at the number of options for each slot. So we have 5 options here, and then 3 options here, and 2 options here. Right. So then what the fundamental counting principle tells us is how to put all those numbers together. Let's see if you can figure it out. Let's say we started with just 3 pairs of pants. Right. So you've got 3 options right now. Well, now you introduce 2 hats into the picture. Right. So for every pair of pants, you have 2 extra options. For the first pair of pants, you can do hat A or B. For the second pair of pants, hat A or B. For the third pair of pants, hat A or B. It doubles your options. Right? You would multiply these together. You would have 3 times 2 total options. And that's what the fundamental counting principle says, is you just multiply these options together. I look at the different slots you have to fill in, the different choices you have to make, the number of options for each one, and multiply them together. As long as you can tell the difference between those, as long as those are completely different things that can't overlap at all. All right, so we've got 15 times 2, we've got 30 total possible options, the fundamental counting principle. All right, so now let's say we've got 10 athletes running in a race. How many ways can we award the gold, silver, and bronze medals? So we can actually do this in the same way. So gold, silver, bronze, that's like first, second, third, right? First, second, and third place, all right? So and these are different, right? You can't win both first and second place. You can tell the difference between second and third place. First and second place, one person's a lot happier than the other person. These are different things. Right? All right. So how many options do we have for the first one? Well, theoretically, any of the 10 athletes could win first place. Right? We'll give them all the benefit of the doubt. But then think about second place now. There's not 10 options anymore. By putting this 10 here, you're saying, okay, one person is going to win first place. Well, once you know who's won first place, that person can't also win second place. So now you would only have 9 options for second place. And then third place, well, you've already picked a first and second place. Those people can't also win the bronze medal. Only 1 medal per person. Let's not get greedy. So now we only have 8 options. And again, fundamental counting principle says multiply those together. So you would have 72 times 10, add the 0, 720 options. Right? There is also a formula that you could use here. This is called permutation. So permutations are where you're trying to arrange things in order. Right? So if we say we have 10 people and we're trying to arrange 3 of them in order, it's called a permutation, and we could use this formula here. So n would be the total, and r would be the number that we're trying to arrange. So we could say we've got 10 people, and we're trying to permute or arrange 3 of them. So it would be 10p3. And you can see the formula right here. Hopefully that makes sense. Notice we started out with the factorial. we started out with the beginning of 10 factorial, but we just chopped out the end because nobody cares about the losers, right? We're only interested in the winners. So the losers, the 7 factorial at the end got chopped off. That's what this denominator would do. This would be the losers, the ones that you're not picking, the ones that you're not arranging, that you're not caring about, are divided off at the beginning. Those get chopped off. This right here is 10 factorial divided by 7 factorial. Okay, but this also is in your calculators is one of the reasons that this formula could be useful here. I don't use it a lot myself personally. I tend to just kind of use the slots thinking to avoid having too many different methods to think about. But the nice thing is this would be in your calculator. So if you would type the 10 first, and then hit your math button, and then we'd be in PRB again, hit the left arrow. The second choice here, NPR. So you would say 10 NPR 3, and there you go, same answer, 720. Okay. So either way you want to do these, either just still use the fundamental counting principle or use the permutations formula. Either way you'll get the same answer. All right, now here's the one where we're going to have to use a different method. Okay, we got 10 people wanting to see a movie, and there's 3 seats left, and we're just trying to see how many ways there are to select who gets the seats, just who's going to get in the theater. Okay, we're not looking at like, you know, maybe one of the seats is closer to the screen, or, you know, maybe there's 2 of the people that want to sit together, and so, you know, how many different orders can we sit to people? We're not looking at that. We're just looking at who's going to get seats, who's going to get into the theater. Okay, so what that means is we can't tell the difference between the 3 seats. There's no difference between them. We're looking at order not mattering here. The other ones, the order matters. Okay, it matters whether you call something a shirt or a hat. It matters whether you call someone first or third place. Order matter. You could tell the difference between these. This one, that's not true. So what we have for this is we have a formula. Right? So this one we can't use fundamental counting principle anymore. We can't use slots because they're not 3 separate slots. We're just picking a group of 3 people. Okay, so this NCR we can read N choose R, and that's kind of the situation you want to use this for. We've got 10 people and we're choosing 3. You could put the 10 names in a hat and pick out 3 names, and it wouldn't matter, you know, if you were the first person or the third person picked. Right? That's when we use this formula, when order doesn't matter. And we have to just use this formula here. We can't use slots. So we just say there's 10 total people, and we're choosing 3 of them. The formula is right here. You could compute it yourself. This is called combinations, by the way. Got permutations and combinations. And so out of 10 people choosing 3, we'll just use our calculator for this one, unless you'd like to crunch it out yourself using that formula right there. Notice it's very similar to the other formula. Basically what happens is we just divide out all the different ways to arrange the ones we are picking. So this R factorial is what we add in. That's the 3 right here. So if we look at, we pick those 3 people, those 3 seats, there's 3 times 2 times 1 ways to arrange people in those 3 seats. So we're just dividing out all the different rearrangements, all the different orders of, of picking those 3 people. But you don't have to worry too much about that. You can just use your calculator if you'd like. Go into your math menu again, go over to PRB again, and then instead of NPR, use NCR, 10 choose 3, and now there's only 120 possibilities. Okay. So just make sure you know the difference between these 2 problems here. Make sure you see the difference. Both of them, there was 10 people, and we were picking 3 of them. Here, the order mattered. You can tell the difference between gold and bronze. Here, the order didn't matter. You can't tell the difference between the 3 people. They all get in the theater. They all get seats. Okay? That's the difference between being able to use slots or NCR. And that's how I usually look at these problems. If order matters, if I can tell the difference, I use the slots method. If order doesn't matter, I use NCR. If you want to throw NPR in there, you can, but I usually look at NCR, order matters, or sorry, NCR over here, NCR over here, order does not matter, slots, order does matter. You can tell the difference between the things. That's kind of your 2 choices for these counting problems. All right, so why don't you give some of them a try then. Take a look at these three problems. You're going to have to look at, does order matter or not? Can you tell the difference between the different things that you're picking? Or are they completely interchangeable? Go ahead and give these three problems a try. All right. So here were the answers. So the first one you could have done using the slots or the NPR. So here it said ordered, so order mattered. So you could either say there's 12 things, I'm arranging 6 of them, that's the NPR. Or you could say there's 12 slots to fill in, 12 choices to be made. And then these were the number of options in each one. Again, it decreases each time once you've picked the first what was this project? Once you pick the first project, it can't also be the second project. So you have one less option each time. Multiply them together. In the second one here, order did not matter. It's just a group of 3 people. Pick the names out of the hat. Doesn't matter if you're the first name drawn or the third name drawn. Either way, you got a job. You're happy. You're making money. All right. So that's when we use NCR. And then here, this is fundamental accounting principle. We have 2 different choices to be made, 2 different slots to fill in. How are we going to go from A to B? How are we going to go from B to C? Number of options for each one. Multiply them together. All right, so that's counting. Let's take a look at probability now. So probability, the basics of it is just the number of ways to get what you're looking for out of the total number of things that can happen. So number of desired outcomes out of number of all the possible outcomes, okay? Assuming these are all equally likely outcomes. And the lowest probability can be 0. That would mean it was impossible. The highest probability would be 1 or 100%, and that means it's guaranteed, definitely going to happen. Okay. We can also take a look at how we combine multiple probabilities together. So if we want A and B to both happen, or A then B, either way, but if they're both have to happen, then we multiply the probabilities together. And is going to mean multiply. And then if it's or, we're going to add those probabilities together. These would have to be mutually exclusive, but the basics is and means multiply, or means add. We're just doing real kind of quick overview, hopefully reminder of probability here. There's a lot more to it. Just kind of making sure that you know or remember the basics of probability. All right, so let's say that we're drawing 2 cards from a standard deck of 52 cards, and we want to find, first of all, let's find the probability that they're both aces. Okay, so if we want both aces, we want an ace and an ace. Okay, so probability of ace and ace, that's going to be the probability of an ace times probability of ace, and is going to mean multiply. Okay, so now we've got 2 different options here. So option A is going to be, we pick our first card out of the deck, we look at it, we hope it's an ace, and then after we've seen that card, we put that card back in the deck, shuffle up the deck, mix it all around, randomize it again, and then draw our second card out of the deck. Okay, let's do that one first. All right, so the probability of the first ace, so we look at how many ways are there to get what we want out of the total. So if you're not familiar with a deck of cards at all, it could be worth Googling that. You will see some problems based on decks of cards. So deck of cards, you've got like spades, clubs, hearts, diamonds for all the different cards. So that's 4 different aces: ace of hearts, ace of diamonds, ace of clubs, ace of spades. So there's 4 different aces in the deck, and there's 52 total cards. So there's the probability for our first ace, 4 out of 52, what we want out of the total. Now the second ace, well, if we're in with replacement land right here, in the with replacement version of this very exciting pull 2 cards game, we've put the card back in the deck, shuffled it all around. That means our second card, the deck is exactly the same. Nothing has changed. So for the second ace, it's still 4 out of 52, as long as we completely, shuffled the deck really well, if it's really randomized. All right, let's see. 4 goes into 52 13 times. So that would be 1 out of 13 squared. So that's 1 out of 169. Not super likely. All right. All right, how about without replacements? All right, so oops, part B now. All right, so the first ace, it would still be the same thing. The first card that we draw, there's 4 aces in the deck, 52 total cards. All right, but the second ace, so now it's without replacement. Okay, so I take my first card out of the deck. I hope it's an ace. I look at it, I see what that card is, and then I put that card aside on the table. And now from the deck to the left, now I try to draw another ace. So now my probability is going to be different, right? My second ace. Now here's the thing. If I didn't get an ace for that first card, I already lost. I'm already out of the game, right? So what I have to do is I have to assume that I got an ace for my first card. Otherwise, I'm already out. So if I got an ace for my first card, now instead of 4 aces left, now there's only 3 aces left. And then is it 3 out of 52? It's not 3. The deck has changed. Remember, I took a card out. There's not 52 total cards. Now there's only 51 total cards. Okay, so when we look at this second probability, we have to assume that the first one already happened. We have to assume that we're getting what we want. Okay? Otherwise, we're out. We're only looking at the possibilities where we actually win, where we're looking for the desired outcomes. We're looking to get what we want. Okay? Let's see. So this one, 4 goes into 52 13 times. 3 goes into 51 17 times. So at that point, you probably need a calculator. I've done it already, though, and it ends up being 221. So 1 out of 221. All right, so even less likely now, right? Even a lower probability. All right, so now what if we want a pair of aces or a pair of kings? Okay, so now we're in or land here. So remember, and means multiply, or means add. So we're going to do the probability of aces plus the probability of kings. This is the notation we use for probability, by the way. This P and then parentheses, that means probability. So back here, this was probability of A and B happening. Okay? So probability of aces plus the probability of kings. Well, we already found the probability of aces. So probability of aces, a pair of aces, 2 aces, both cards being aces. For part A, the with replacement was 1 out of 169. Okay, well, kings, there's 4 kings in the deck too, right? All this math that we did is going to be exactly the same thing, whether it was an ace or a king. Okay, so probability of 2 kings is also going to be 1 out of 169. So 2 out of 169. And then here it's just going to be to this. It's going to be 1 out of 221, 1 out of 221, 2 out of 221. Okay. Just again, it has to be that they're mutually exclusive. So what that means is, there's no places where you're double counting. Like, if you had a card that had like both an A and a K on it, it was a like ace/king, then you'd be double counting it. You would be counting it once in here and again in here, and so you'd have to subtract out all the possibilities that you were double counting. So like if I asked you the probability of a heart face card, a heart or a face card. If we wanted a heart or a face card, then we'd look at hearts plus face cards, but then we'd have to subtract the ones where they were both a heart and a face card. But again, we're just doing a real quick overview, so you're not even going to see that in your problems here. Just for your information, so you know that is required for this whole or probability problems. And then just last real quick here, let's say we have the probability of it raining tomorrow is 0.7. So is it more likely that it will rain or that it will not rain? Well, 0.7 probably seems like a small number because you're used to seeing probabilities as percents. So if we give it to you as a decimal, just realize that you'd want to switch it to a percent for you to probably understand what's going on here. 0.7, that equals 70%, right? Remember, percents move the decimal twice. So 70%, that's a pretty good chance, right? It's more likely that it will rain. because this probability is greater than 50%. Right? And so notice here, again, for this number of desired outcomes out of all the possible outcomes, that's only if they're equally likely. Sometimes people get into the error of thinking that, oh, there's two possibilities, so it's 50-50. Oh, it'll rain or it'll not rain. There's 50-50 chances. Is, one chance out of two possibilities. No, that's only if they're equally likely. Okay. Yes, there's one option out of two total possible options, but one option here was more likely. So this basic way of thinking only works if you've got equal chance of each one of the outcomes. Okay, and then of course if it's a 70% chance of raining, that means it's only a 30% chance that it will not rain. Probabilities have to add up to 100%. Right? That's all the things that can happen are 100%. So there's your quick overview of statistics there. We do have an AP statistics course. If you did that, you'd see a little bit more of this kind of stuff, but a lot more of analyzing data, things of if you take surveys or do those different things. If you have a lot of numbers, a lot of data, how do you analyze those kind of things? There's a lot of the stuff that you would see in AP statistics, but we're in pre-calculus, so we won't do too much of statistics. This will be all we do for stats.